t square minus 1 upon t square plus 1 dt plus d by dx integration c to 3x t square minus 1 t square plus 1 into dt. Continue last step, equal to is d the applying chain rule for the fundamental theorem of calculus. We have the result minus this t square is replaced by 2x. That's why result is 2x square minus 1 divided by 2x square plus 1 and differentiate 2x with respect to x plus for the second part this t is replaced by 3x. That's why 3x square minus 1 divided by 3x square 3x whole square plus 1 d by dx 3x, and so the last result is minus 2x square minus 1 2x square plus 1. Here 2 is derivative of 2x plus derivative of 3x is 3 into 3x square minus 1 divided by 3x square plus 1. Okay, this way we can solve or we can differentiate the integration where both the limits are function of x. Okay. Now we have similar example. Okay, next one. Now we are going to state the fundamental theorem of calculus part 2, which is a last part of this session. The formal statement: if f is continuous on closed interval ab, then integration a to b ft dt equal to capital F of b minus capital F of a, where f is antiderivative of f, that is f dash x is equal to fx. This statement gives us easy way to evaluate definite integral. Here definite integral is integration a to b ft dt. This definite integral has value f of b minus f of a, where capital F x is a antiderivative of small f, that means f dash x is equal to fx. Using this result we can solve some definite integrations or definite integrals. First example, evaluate integration 1 to 2x dx. Integration 1 to 2x dx. It's the easiest problem to understand the application of fundamental theorem of calculus part 2. Evaluate the integration or find the integration 1 to 2 x dx. The integration of x is x square by 2, or this x is a derivative of x square by 2. Evaluate this x square by 2 for the limit 1 to 2. Using fundamental theorem of calculus part 2, the statement says that this value of integration is nothing but difference of antiderivative of difference of the value of antiderivative. The difference of upper limit minus lower limit. The upper limit is 2 square, that means x replaced by upper limit 2, this is 2 into 2 square divided by 2 minus 1 square divided by 2 is equal to 2 minus 1 by 2, result is 3 by 2. Okay, that means we can easily evaluate this definite integral by using the simple concept of antiderivative. That means x is a antiderivative of x square by 2 and the value of integration is nothing but the difference of the values of antiderivative x square by difference of the values of x square by 2, that is 2 by 2 square minus 2 square by 2 minus 1 square by 2, and the result is 3 by 2. Just look at this slide. This is a geometric representation of example. The y is the red line, straight red line shows the function fx, and the green shaded part is the value of definite integral 1 to 2 x dx. And the second part of the graph, the fx equal to x square by 2, it's a graph of antiderivative and the value is f2 minus f1. Here there is a geometric representation of second fundamental theorem of calculus. One more example, evaluate integration 1 to 2 4x minus x cube dx, and using antiderivative concept, the 4x is integration is 2x square minus x square x raised to 4 by 4. Evaluate this result for up in the limit between the limit 1 to 2, and result is 2.25. Similarly, we have another explanation of example, that is geometric explanation. The green shaded portion give the value of integration, and in the second part, in the second graph, we have the graph of antiderivative function fx equal to 2x square minus x raised to 4 by 4, and the value of the difference in the value f2 minus f1 gives the value of that green shaded area. Now next example. In the next example, evaluate integration minus 5 to 5 2 by x cube dx. First of all, as we mention or as we state the fundamental theorem of calculus part 2, this theorem is only applicable for the function f which is continuous on the closed interval ab. That means if function is not continuous, then we cannot use the second fundamental theorem of calculus to evaluate definite integral. Just look at this example. Evaluate minus 5 to 5 2 upon x cube dx. This function fx equal to 2 upon x cube or 2 divided by x cube is discontinuous at x equal to 0. That means if x equal to 0, the value of function fx is infinitive, which shows that the function fx is discontinuous at 0, and so we cannot apply the fundamental theorem of calculus to evaluate this limit, and so this integration does not exist for the fundamental theorem of calculus. It's a counter example for the fundamental theorem of calculus. That means fundamental theorem of calculus part 2 is applicable only continuous function. If function is discontinuous, then we cannot integrate such function using fundamental theorem of calculus. Now we have some more example which clear the concept of continuity and discontinuity. Just look at the example. Integration 0 to 2 fx dx, where fx is equal to x raised to 4 if 0 less than equal to x less than 1. And second, fx has second definition, x raised to 5 when x lies between 1 to 2. Before applying fundamental theorem of calculus, we have to check the continuity of function. If function is continuous, then we can apply the fundamental theorem of calculus. Just look at the definition of function. The definition of function is fx equal to, place camera on the table. Okay. Here fx is equal to x raised to 4 when x is lies between 0 and 1, and x raised to 5 when x is lies between 1 to 2. In this case, the function has a value, the function, we have to check the continuity of function at x equal to 1. We have to check the continuity of function at x equal to 1. Here for f of 1, we have two values. For f of 1, x equal to, if limit f of 1 plus the value is 1 raised to 5 equal to 1, and f of 1 minus the value is 1 raised to 4 equal to 1, this implies f of 1 plus 1 equal to f of 1 minus. That's why f is continuous at x equal to 1. Here f is continuous, so we can apply fundamental theorem of calculus to evaluate this integration or definite integration 0 to 2 fx dx. Now to evaluate the integration, we have to divide integration into two parts, 0 to 1 plus 1 to 2. Between 0 to 1, the definition of function is x raised to 4 dx, and between 1 to 2, the definition function is x raised to 5 dx, equal to, the integration 0 to 1 is, using concept of antiderivative, the x raised to 4, the antiderivative of x raised to 4 is x raised to 5 by 5, 0 to 1, and antiderivative of x raised to 5 is x raised to 6 by 6, 1 to 2. The second part of fundamental theorem of calculus says that its value is 1 raised to 5 by 5 minus 0 f of b minus f of a plus 2 raised to 6 by 6 minus 1 raised to 6 by 6. Clear? Then the last result is 1 by 5 plus 64 minus 1 by 6 is equal to, result is 1 by 5 plus 63 by 6 is equal to 21 by 2, and result is 107 by 10. 107 by 10. That means in this example, the function is look like discontinuous, but after checking the continuity, we can show that function is continuous at x equal to 1, and that's why we can apply fundamental theorem of calculus and we can evaluate the limit of such functions. Limit of such functions. Clear? Okay, that means in the today's session we have understand the fundamental theorem of calculus, we start with its physical intuition, geometric intuition, and that both the intuition shows that the integration and differentiation are inverse processes, and this both the concept integration and differentiations are the fundamental concept of calculus. That's why this theorem is called the fundamental theorem of calculus. Okay, this way we have finished our lectures. Okay, thank you very much.